His research interests are experimental quantum optics, quantum sensing, quantum enhanced imaging, quantum plasmonic sensors, bright squeeze states, electromagnetically induced transparency, orbital angular momentum of light, among many others. So today he's going to speak about encoding information in spatial correlations of bright entangled light beams. Dr. Ashok Kumar, the floor is yours.
Yeah. Thank you, Dr. Joy. Yes.
Yeah. And you may share your slide and start.
Yeah, I will do it. Can you see my slide?
Yes, it's visible. Maybe you can make it full screen.
Okay. Yeah, is it fine?
Yeah. Yeah.
Okay, thank you. I would like to thank the organizers for inviting me here. So what I'll be talking today, I'll be talking about, the title I kept like encoding information in spatial correlation of bright entangled beams. But I would like to emphasize the fact that my talk won't be covering only this specific aspects. So what I would like to give you, because I noticed that there are a lot of students here. So what I want to give an overview of spatial quantum correlations. And then at the end, I would like to talk about how we use these spatial quantum correlations for information encoding actually. So to start with, so I will begin with a motivation that why we are interested in spatial quantum correlation actually. So of course they have twofold advantages. One is in a technological point of view, they are applicable in many of the quantum technologies. For example, they are useful in quantum imaging, quantum sensing, quantum cryptography, and many more. And on the other hand, for fundamental point of view, they provide a nice test ground for entanglement testing or Einstein-Podolsky-Rosen paradox actually. So we can do fundamental science as well as quantum technology with those spatial quantum correlations. Moreover, if you are interested to know more about it, I would like to flash 3 review articles over in the difference appeared in the difference of 10 years. This is 99, this is 2010, and this is 2020. You can look at how over the time this research in this direction has progressed. So with this motivation, I would like to tell you what is the outline of my talk. So I'll be talking about, basically first I'll be introducing what do we mean by spatial quantum correlations. And then I'll talk about some of the spatial quantum correlation studies that has been done in this parametric ground conversion. And of course, I'll talk about some applications and limitations. And then finally, I'll come to the bright entangled light beams that I do work on it. And then basically I will talk about how do we generate those beams, and then how do we study the spatial quantum correlations in those beams, and then finally how we can do fundamental science as well as technological aspects with those beams. So I will cover with this motivation my talk. So to start now, coming to the quantum correlations actually. So of course, I said spatial quantum correlation, that means there has to be temporal also actually. So what do we mean by temporal correlation? If you look at most of the experimental quantum optics or quantum optical experiments, so what these experiments deal, they deal with the temporal arrival of photons actually. What does it mean? It means that let's say you have a pair of photons. You have a source that creates a pair of photons, and then you detect these photons with detectors, let's say single photon detectors. Then what you are basically interested in those studies, you are interested in the arrival time of photon over time actually. Basically, you will get a time series data, how photons are arriving at different time, and then what are their correlations over the time actually. So that's kind of study will give you kind of temporal correlation. On the other hand, the spatial quantum correlation, we don't care about how the photons are arriving over different times. What we do care about, we care about how the photons are arriving on a transverse plane, which is perpendicular to the direction of propagation. propagation. Let's say I have a twin beams or twin photons which are emitting. If I look at a transverse plane or perpendicular to the propagation direction, how the distribution of the photons in that transverse plane actually. So I'm interested in that actually. That's what in this kind of distribution, how their correlations are distributed. This kind of correlation will give me spatial information or a spatial correlation. So we want to study or we want to use this kind of correlations. Now, the important point is, of course, I have introduced the spatial quantum correlations. So now important point is, how do we generate those pair of photons actually? Of course, there are many techniques. And then, of course, the most prominent technique that we use by the nonlinear optical interaction actually. So you know that when you shine a laser or electric light to a medium, then you polarize your medium actually. Basically, the polarization induced in a medium can depend on the first or higher power of your fields also. So see what these higher power you see here, these higher powers are responsible for creation of pair of photons actually. And then, you know, the most conventionally used methods for creating pair of photon, which are based on this QIQT and QIQT3, they are known as spontaneous parametric gun conversion or Fourier mixing. So if you look at, you know, if you look at the spontaneous parametric gun conversion, I would say more than 99 or 95% people working in the experimental quantum optics, they deal with this kind of system actually. In that system, what we do, we basically, this is a 3-photon process. You interact a strong laser beam with a nonlinear optical crystal, and you create a pair of photons actually. And since, of course, this creation has to conserve the conservation laws of nature, so they have to conserve the energy conservation, they have to conserve the momentum conservation. Now coming to the spatial quantum correlation properties of those beams. So where do they appear, or how do I perceive spatial quantum correlation in this kind of experiments? So if you see here, then you know that you shine laser beam, you create a pair of photon. And basically you create pair of photon at one single point. You know, at one point, a photon is created into two actually. So basically the pairs that you have created, they have a common birth zone actually. This common birth zone gives position correlation to those photons. On the other hand, if you look at how these photons will propagate over the longer distance, that will be covered by this momentum conservation. You know that the total momentum of this one has to be equal to sum of these two actually. So that decides which direction they will go. Basically, that momentum conservation gives the momentum correlation to those photons actually. Now coming to you know, this is kind of fundamentally how position and momentum correlations are coming to these photons. But now in lab, being an experimentalist, I want to check that in the lab. So how do we check that these position correlation and momentum correlation? And for that, you can use simple optical system. Basically, to look at the position correlation, you can use an imaging system that images the birth zone of photon to your detection plane. That's how you can get the position correlation information. As I said, the position correlation is because of the common birth zone. Basically, effectively, you are imaging the birth zone to your detection plane and then looking at the position correlations. On the other hand, momentum correlations can be mapped to your detection plane by using Fourier lenses. As you know that, you know, the lens has a very important properties that if you put a lens into F to F configuration, it gives the Fourier transform of whatever is input plane at your output plane, at your far field or Fourier plane. That's how you can convert this position momentum or position correlations to the momentum correlation, or that's how you can get the momentum correlation information. So that's how you can obtain position and momentum correlation at your detection plane. Now, having said that, as I said, these kind of spatial quantum correlations has a lot of significance in the fundamental science. For example, to study or to look at the Einstein-Podolsky-Rosen paradox. So what it is, or how it is useful, how this spatial quantum correlation will be useful, I will be highlighting that in a couple of slides. So as you, by now, you must be aware of that, in 1935, Einstein-Podolsky and Rosen wrote one of the most influential or controversial paper of 20th century, actually. Basically, they question about the validity of quantum mechanics, actually. What their experiments still, basically, it was a thought experiment. In that thought experiment, what they considered a pair of particles which are correlated in, which has a perfect correlations in their positions and momentum, and then I have a pair of particles which are perfectly correlated in their position and momentum, and I keep them like space-like separated. Space-like separated means if you want to have a communication, you have to have instant communication, you have to have a speed greater than speed of light, actually. So what it was, if you do the quantum mechanical calculation for this kind of scenario, what appears that, what they found that, it appears that this kind of scenario seems to violate the Heisenberg uncertainty principle, which is basically EPR paradox. So how it appears, I will tell you that. So in principle, actually, if I write the mathematically, it's just simple quantum mechanics. If I write the state that EPR thought, if you write that state in the position basis, let's say A and B are my two particles, and then I can write that state which has perfect correlation in their position and momentum like this. That means if I do the measurement on position of particle A, let's say I get X prime measurement, then definitely I can predict the position of particle B as X prime. The same state I can write in the momentum basis, just the basis transformation of basic quantum mechanics. Then it turns out that if you write the same state in the momentum basis, also it turns out that there's a perfect correlation in the momentum of those particles, actually. So that means that means by doing the measurement on particle A, I can infer the position of the particle B, which is space-like separated. And the same thing, by making the measurement on momentum of particle B, I can infer with certainty what is the momentum of particle B. So since what Einstein EPR thought that there is no instant communication should happen, so what they thought that it appears that the particle B, which is space-like separated, is having already precise position and momentum, actually, which is against the spirit of Heisenberg uncertainty principle, actually. That's all about the paradox. And of course, we thought later on it was found that this is not completely true, because what in the quantum mechanics it was found that what Einstein EPR thought, EPR considered the local realism of consider quantum mechanics as local theory, but now we know that quantum mechanics is non-local and it can show this kind of prediction. So now, having said that, now okay, this is just about the EPR paradox. Now, if I want to show this EPR paradox in lab, or if I want to create a scenario like EPR paradox in lab, so what are the criterion, actually? What I have to satisfy, or what kind of measurement, or what kind of output I have to get to say that I am in an EPR paradox regime? For that, in late 80s, Red and Drummond, they proposed a criteria. They said that if, let's say, you have two distant particles and you are making measurement only on particle A, and then from that measurement, you are inferring the properties of other particle which may be far apart, actually. So in that case, what you do, you are making measurement on system A only. From that measurement, you are inferring what is the uncertainty in the measurement of other particles. For example, if you do the measurement on the position or measurement uncertainty, or inferred measurement uncertainty is this one, and then inferred uncertainty in momentum is this one. If you look at the inferred uncertainty product, or is also sometimes known as conditional uncertainty product, if it is coming less than h bar square by 4, then you say that you are satisfying the EPR argument. And then the experimental verification of this kind of scenario in the continuous variable, basically along the spirit of EPR, was demonstrated by Jeff Kimball and his group in 1992. And then in that experiment, they, instead of looking the position momentum, they look at the quadrature operator of the field actually. Now the coming to the actual realization. Actual realization means EPR paradox in its original form was demonstrated by Robert Boyd group in 2004, where he has shown the EPR paradox in its original form. Original form means in terms of the position and momentum variables. So what he did basically, or his group did basically, they looked at the photon pairs created by the BB by spontaneous parametric down conversion process. They looked, or they may map to the position correlation by using an imaging system to their detection plane. That's how they obtain the position correlation. Basically, they fix one detector and then scan the other detector and look at the correlation between the arrival of the photon over the position. And then the far field correlation, for the far field correlation, they developed a far field system, basically a Fourier lens, which basically Fourier transformed the BBO crystal to their detection plane, and they did the same measurement. And with that, they got the correlation, basically position correlation and momentum correlation like this. And from there, the uncertainty in position and uncertainty in momentum correlation, basically they are conditional or inferred uncertainty. And then their product, they have obtained like 0.01 h bar square, which is definitely less than h bar square by 4. So that's how they looked, or they demonstrated original EPR paradox in the lab experiment. So now, of course, having said that, this is, as I said, this is a fundamental experiment actually. Later on, people have used this kind of system for application purpose actually. So I would like to show just one example where people have shown this spatial quantum correlation for the application, for example, quantum imaging actually. So this is done in 2009 by an Italian group. So what they did, they basically, they have again spontaneous parametric down conversion, photon pairs created by spontaneous parametric down conversion, and they look, or they basically look at the far field. Basically, they use a Fourier lens, and they looked at they basically map these position correlation to momentum correlation on a CCD actually. So instead of just scanning other detector, they project whole beam on the EMCCD camera. And then what they said that, since there are position correlations, then the manifestation of position correlation could be if you look at the noise difference between or spatial noise, basically how the photons are arriving, the spatial at the different spatial regions. If you look at the spatial noise in these two beams, it can be cancelled because of these quantum correlations. So what exactly they did? They defined a parameter called noise ratio, basically, which measures the difference, variance of the difference noise actually. Since the two photons arriving here, their positions are correlated. So what they did, they look at they capture one image here, and they look at the difference of these two images, and there, whatever the common correlated noise, you can cancel it out. And they basically define this noise ratio, which is basically variance divided by mean. And you know that for the coherent state, it has to be 1, that is called short noise limit. But for the quantum states, like the states generated by the SPDC process, they could get this noise ratio less than 1 actually. So that means they can get this advantage in the noise reduction, because classically, or with our all classical scheme, we can go up to short noise limit actually. But in this kind of scenario, they can get the noise ratio, or basically noise in your beam or your spatial profile less than that is allowed by the short noise limit. Moreover, this is just a demonstration, but very recently the same group have demonstrated that this kind of experiment, this kind of noise reduction can be implemented in kind of quantum noise in a quantum imaging scenario, where if you place one object in one path of your beam, and then you image that by using your imaging lens on an EMCCD camera actually. And then if you directly measure this, if you directly measure the or look at the image of the object, you get like the image like this actually. And on the other hand, if you do some kind of classical differential measurement, you do image like this. But at the same time, if you do imaging of this object by using the quantum correlated beam, then you can get really enhanced contrast or enhanced resolution in your image. So the central idea is, there is an image, but it has a lot of background noise actually. So that background noise is subtracted by using another reference beam, and then because since these are the quantum correlated beam, their noises are also correlated actually. So if you subtract out the correlated noise, then you can you can enhance the imaging scenario and enhance the resolution of your object that you want to image. That's how they have worked out it. So one thing I would like to tell you that these initial experiments with the SPDC photon source, of course, they have provided a significant insight on spatial quantum correlation, and of course, they have demonstrated the quantum enhanced imaging and other sensing experiments also. But one of the main drawback in those experiments are they are really single photon regime actually. So you have to take thousands of images, hundreds of thousands of images to get this kind of pattern. So you have to acquire maybe millions of images to millions of shots in your CCD camera to have this one. So that is one of the limitations of those experiments. Now of course, a natural question is, can we have spatial quantum correlation with a large number of photons, or mainly macroscopic regime? Macroscopic regime, when I mean to say that where you can see really your beam is no longer a single photon regime, where you have to have a sophisticated single photon detectors actually. So to address this question is, yes, we can use bright twin beams light generated with the four-way mixing in hot atomic vapor to look at or to remove some of the main drawbacks of the SPDC photon pairs. So how this method works, I will tell you about that, and then remaining talk will be focused on some of our experiments or experimental research that has used the beams, bright twin beams generated with four-way mixing experiments. So what in this experiment we basically do, we interact a strong laser beam and a weak beam in an atomic medium. Basically, we take rubidium vapor, and then in that rubidium vapor, we just make some configuration that called double lambda configuration. Basically, what we do in this atomic system, we absorb 2 photons from our laser beam, and due to energy conservation, we emit 2 photons. And then in the presence of this input probe beam, this process we amplify. This process gets stimulated or amplified, and that in turn generates bright beams actually. That is the whole idea actually. Basically, you can do spontaneous four-way mixing also. To stimulate this process, we start with some input seed beam, and then stimulate the process, and at the end you can get bright twin beams actually. So with those bright twin beams, it has some significant advantages, as you can say that you can see that if instead of a single photon pairs, if I have a stream of photons or a bunch of photons coming together, then we can get statistically significant results in noise reduction in very small number of images. Moreover, the signal to noise ratio in quantum enhancing and quantum enhanced sensing and imaging scales at √n. So more the photons you have, better is your signal to noise ratio. That's how you can win by using the bright twin beams. And on the other hand, we are generating these bright twin photons with the atomic system actually. So that can have another added advantage, that if you want to, in future, if somebody wants to work with, you want to store these kind of photons in the quantum memories which are based on the atomic system, then these photons can be compatible with the atomic based quantum memories actually. And this is like from practical perspectives, it has a lot of significance. And on the fundamental perspective also, it is like a significant, because thing is, most of the quantum optical experiments are done with a single photon regime. So how things are changing from moving to single photon regime to a bright regime, that is some interesting avenue that we are looking at. And then over the past few years, we have done a lot of study along these directions, starting from first experiment where we show that, of course, we can observe spatial quantum correlations with those beams. And with our very recent work, where we have used those beams something along the line of quantum cryptography actually, where you can encode information in those beams actually. That is now in Science Advances. So hopefully in a couple of weeks it will be out. So with that, I would like to now focus on how do we study spatial quantum correlation properties on our system. So as earlier I said, when we have spatial quantum correlation properties, we look at the position or momentum correlation. And moreover, if you look at the momentum correlation, they are directed, or they are basically governed by the phase matching condition actually. So here, opposite to spontaneous parametric conversion, where one photon was converted into two, here two photons are converted into two actually. Sum of the momentum of two has to be sum of momentum of these two actually. And then with this typical phase matching condition is given like this, and it has a kind of sync profile actually. What does sync profile means? Sync profile means that if it is not even zero, still there is some efficiency, or there is still some efficiency of generation of photons actually. That means there is a tolerance, there is some tolerance on delta K actually. So that tolerance is interesting in our aspects, that if delta K was zero, if delta K was zero, then you are just getting point-to-point correlation. But since there is some tolerance on delta K, there can be some tolerance on delta K. That means the photons that you are creating with your nonlinear optical interaction, it will emit photon on a cone which has certain width actually. You can have photon which are correlated in this region actually, or there are multi-modes actually. It's not just a single spatial mode. You have multi-modes actually. And then in some of the earlier studies, people have shown that this kind of system supports images actually. They support the multimode. What I mean by multimode, that you can put some mask or some imaging, some mask, some pattern to one of your seeding beam, and then you can transfer that pattern here and here. You can basically generate your probe and conjugate, or your twin photons or twin beams with arbitrary spatial pattern actually, which is not present. Other regime where people work with the bright entangled photons or entangled beams is with using cavity actually. Cavity can also generate entangled photons in the bright regime, but in the cavity you can't have this kind of freedom actually. You will not have the multi-spatial mode actually. So for the quantum imaging kind of experiment, this provides an ideal avenue actually. So having said that, how in lab we have done the spatial quantum correlation of the bright beams. So for that, what we have done, so I will explore here. Now the experiments are similar to what the SPDC people have done. So this part is basically for the generation of bright beams, as I discussed actually. We interact a pump beam and input weak probe beam inside a atomic medium, and then generate probe and conjugate, which are bright beams actually. And then here in this particular experiment, we have looked at the far field correlations. That means we have used an imaging system. We have used a lens system that is kept in F to F configuration actually. And then we have recorded the images of our pump and our probe and conjugate, we call probe and conjugate this generated beams on a CCD camera actually. And of course, care has to be taken while acquiring images on a CCD camera. So for that, we have used we have pulsed our pump and probe beam, and then this is our pulse sequence actually. So we basically what we do, we created pulse of probe and conjugate beam, and we acquired these pulses on an EMCCD camera. And this EMCCD camera we use in a fast kinetic mode where 2 frames are acquired. 2 frames of, this is conjugate, this is probe. These beams are acquired in an interval of 2 frames are acquired in an interval of about 60 microseconds actually. Now, what we are interested, as I said, we are interested between the quantum correlation of the noise of this and noise of this. Okay, this is a beam. This is the image of the beam, but it has a bright DC background actually. What we did, we subtracted this DC background by doing the difference measurement. We subtracted the frame acquired in 2 consecutive images, and then we got we obtained the noise of basically intensity noise in this beam and intensity noise in this beam actually. And once we have obtained the intensity noise in this beam, then we can look at the noise reduction or quantum correlation or whatever things you are interested in. But one thing we have to note that since we are looking in a far field correlation, and then that due to phase matching condition, the correlated region probe of our twin photons, they lie in a diametrically opposite side actually. So to subtract it, so what we did, we rotate one of the image by 80 degrees. We subtract these 2 images. This is the probe noise. This is the noise, intensity noise in one of the beam. This is the intensity noise in the other beams. So we subtracted those to see that whether we have intensity noise reduction or not. So basically, when we subtracted it, then we got this kind of pattern, and ultimately we looked at this ratio, which is variance divided by mean. And as a result, we got some result like this. So this is for the typical laser beam actually, for which we are limited up to short noise actually. Our noise ratio has to be, it is 1 for the laser or for a coherent state. But for the state that we have worked with, we have reduced the noise beyond the short noise limit actually. So that's how we have obtained noise reduction in spatial domain, or we call that spatial squeeze. On the other hand, when we don't rotate, because thing is we are subtracting this with this one. So basically we are subtracting the correlated noise. Once we subtract the correlated noise, we get reduced noise. On the other hand, if we don't subtract the correlated noise, then we should get excess noise that we have verified. If we don't rotate one of the beam with respect to other, we can get excess noise actually. This is a sanity check. On the other hand, one important aspect here we have to look at it is, if we want to look at whether the correlation of this beam and this beam, it is a point to point or point to area. For that, we did some kind of cross correlation measurement. For that, what we did, we basically select one small region in one beam and scan that region with the other beam actually. We select one area and look at the cross correlation of this with other beam, and then scan over the whole beam actually. And then as a result, what we saw that for probe and conjugate or twin beams that we have generated, we got a typical scale of correlation. That typical scale of correlation we call as a coherence area actually. And then for our experiment, it came about 10 by 10 pixels. And on the other end, if you do the same experiment with the laser beam, there are no correlations. So you don't expect any correlation or any cross correlation results with the typical laser beam. So that's how we have looked at the spatial quantum correlation of properties of bright twin beams. Now, having studied those, now our next motivation was, okay, we can demonstrate this spatial quantum correlation. Then now the next thing is, can we create EPR paradox kind of scenario with our bright twin beams? Basically, can we violate this kind of relation? Actually, these are the conditional uncertainty product or inferred uncertainty product. Actually. And that in the next work we did that. Yes, indeed, these beams can create this kind of EPR kind of scenario. For that, the experimental scenario is same as what Robert Boyd done in earlier experiment with the SPDC. So we have to look at near field correlation. For that, we have to design an imaging system that images the birth zone of these beams, and then in the far field, for the momentum correlation, we have to look at the Fourier transform of their birth zone. So we recorded the image in the near field and far field, and we did the same analysis what we did in the spatial quantum noise reduction. As a result, here also in the near field also we could see the correlation, and far field we could also see the correlations. Basically, near field correlation will give me the information of the position correlation, basically delta square Rx, and on the other hand, far field correlation will give me the momentum correlation, or basically the width will give me uncertainty in the momentum distribution of photons actually. And then what we found, we calculated the uncertainty product, and ultimately we definitely got less than what is needed to violate the conditional uncertainty product. So thus we claim that we can show the EPR paradox in this kind of beam. Moreover, one interesting thing, as I was motivating you, that why we are looking at with the bright twin beams, even if there are the similar studies exist in the SPDC. So now my claim was, we can show this kind of statistically significant result just with a few number of images. So here we have looked at, looked at the uncertainty product for very less number of images ranging from 5 to 200. Even with the 5 images, we could see, or we could demonstrate the EPR paradox actually. So this is the limit. We are far away from the limit. That's how these kind of experiments will help you. Moreover, as another measure is, we have demonstrated the spatial entanglement in this kind of beams. Basically, spatial entanglement means position and momentum entanglement in those beams. For that, we have satisfied the DGCZ criteria. Basically, we looked at as I said, we look at the noise reduction, basically squeezing in the near field as well as far field. And then what we saw, according to Duan criteria, for the for satisfying the entanglement, your inseparability parameter has to be less than 2, and we got 0.67 or 0.63. That proves that indeed these beams can show EPR kind of paradox or spatial entanglement. So having verified these things, they are showing the EPR kind of paradox, and as well as they can show the spatial entanglement. So now the latter goal was, since we said that these beams can support a large number of spatial mode. So now our goal is, or what we wanted to look at, can we use this kind of beams for spatial information encoding actually? Can you encrypt some information in those beams? That question we try to address. So the setup is similar what we did in the earlier, but what we did, instead of just using a mirror there, we replaced mirror by an SLM, a spatial light modulator. And then what we did, now the goal is we want to encrypt some information. We want to encrypt some spatial information in those beams actually. So for that, the more elaborated figure is here. So we use an SLM in the POM beam actually. And then let's say we want to encode some spatial pattern actually. So then for that, we created a hologram for that. And that hologram, this is basically a phase hologram. And we imprinted that hologram on the SLM. And then we image this hologram. Basically, we image the pattern that is encoded to beam to the cell actually. And then finally we did the Fourier transform of this, or we looked at the things at the far field. At the far field, basically we should get the information of this object. So the whole idea is we wanted to encrypt this information in the twin beams actually. Okay, that was the whole idea actually. So for that, so what I would show that some of the results that we have achieved. So we use basically two spatial patterns, and these are the corresponding holograms. And then these are the one interesting thing is, if you look at, you encrypted some information in the pump, and you want to see that whether that encrypted information is shared between the twin beams that you have created actually. So indeed, if you look at their just DC profile, if you look at just their images, you don't see any pattern actually. But if you look at the cross correlation, if you do the cross correlation measurement between these twin beams, then what you see, you can see the encoded pattern. So these are the target pattern that we wanted to encrypt. These are the simulated results that we were expecting, and these are the experimental results. So you can see that we can clearly demonstrate, or we can clearly decrypt the information that we have encrypted in our system. So on the other hand, of course, this can have application in quantum cryptography and quantum communication actually. So now the natural question is, can anybody, so if thing is, I'm saying that to decrypt that information, you have to look at the cross correlation. Now the question is, if somebody has only this one or only this one, then if he or she can detect it or not actually. For that, we did the analysis, and indeed we found that the answer is not actually. So we cannot decrypt the information what was encrypted. So this was the autocorrelation of the probe conjugate, and this was the simulation. So this is not giving, or this is not revealing the information that we have encrypted actually. So that's how it can have application in secure quantum communication or secure quantum cryptography. So moreover, we did more control over that. Not only encryption, you can control over the pattern that you have created actually. For that, what we did, we did some, some very smart things. So the four-way mixing process, as I said earlier, it involves two pump photons and two probe photons, two twin photons rather, probe and conjugate actually. And of course, they have to satisfy this kind of phase relations actually. And then what we did, by changing the relative phase between probe and conjugate photon, you can control the cross correlation pattern. Basically, you can, let's say you are getting if there is a zero phase between probe and conjugate, and if you change that phase to pi/2, you can get the negative of this. And by changing that phase between probe and conjugate, you can basically hide this even within the cross correlation, hide the encrypted information in the cross correlation measurement. Moreover, now one natural question will come. Of course, you did this cross correlation measurement, you encrypted information in both the beams. Of course, it is not available in the single beam, but how do you claim that it is quantum actually? So that is another question we have tried to address. For that, what we did some temporal measurement. Some temporal measurement means we did some squeezing measurement, basically intensity difference squeezing measurement with the different spatial pattern. So what I mean by saying that, so instead of EMCCD camera, we just replace, or you can use a flip mirror. You can use just a flip mirror and then detect these beams on a photo detector and look at the intensity difference squeezing. And then it turns out that these beams with having the spatial profile in their beam. So if you look at, this was our short noise limit. This red trace was the squeezing or our squeezing without any pattern actually. And then this green and blue traces were with two different patterns that you have used. So with those all patterns, the spatial squeezing or sorry, temporal squeezing or intensity difference squeezing was persistent actually. That means the quantum natures or is even persistent there actually. That's how we have verified that there is indeed quantum correlation present in those beams. So with this, I would like to conclude my talk. So what I discussed in last 45 minutes, so I talked about, spatial quantum correlation properties. How do we generate those, or how traditionally people have used the SPDC photon source to learn the spatial quantum correlations actually. Moreover, now then I said, we work on the bright twin beams, and then of course we use four-way mixing in hot atomic media, hot atomic vapor to create these kind of beams, and then study the spatial quantum correlation or the EPR paradox kind of situation with the original position and momentum degrees of freedom in the bright regime. Moreover, the last but not least, what we have shown that these spatial quantum correlations can indeed be useful for quantum cryptography and quantum communication. And then, of course, it just opens a path toward secure high capacity information encoding and information processing. So with this, I would like to acknowledge the people with whom I have collaborated, who have contributed. So Alberto Marino, who was in University of Oklahoma, now moved to Oak Ridge National Lab, and the collaborator with whom I have worked, and then my PhD students at IST. And with this, I would like to thank you. And if you have any questions, I would be happy to take it. Thank you.
Hello, the floor is open for questions now.
Yeah, there is a question I see in chat box that says that I don't understand a thing. Measuring at one region, I can infer the measurement result at the other position. This is in fact true in classical Newtonian case. What the paradox then? For example, if a bomb explodes and two of its fragment can go different ways, then by measuring the momentum, one can infer the measurement of the other. Okay, so I understand that what you are saying, what we are talking about, that if we are talking about the state of a system, actually we are talking about the quantum particle or quantum system. So if you can't talk, when you talk about the microscopic particle, you can't relate with the classical Newtonian mechanics actually, where the Heisenberg uncertainty is almost negligible actually. Uncertainty product is negligible. Here, what I was telling you, when you talk about the EPR paradox, so what I think you need to look at EPR paradox, what it says actually. So I have a pair of particles which are perfectly correlated in their position and momentum, and then if I make them space-like separated, and then if I do the measurement on the particle which is in my lab and other particle which is space-like separated actually. If I make a measurement on a position of particle, I could infer the position of the other particle. And then on the other hand, if I do the measurement on the particle, I could infer the position of momentum of the other particle, which is far apart from me actually. So what it appears, or what their logic was, since they are space-like separated, there is no instantaneous communication happening. So since sitting in my lab, I can infer the position and momentum of other particle which is infinitely distance away from me. That means it appeared that the other particle which is infinite distance away from me is carrying definite position and momentum actually. That's how the whole paradox is. That's how this paradox is all about actually. It has definite position. It appears that it is carrying definite position and momentum actually. So or the uncertainty product is kind of zero actually. That it appeared to be by applying the local theory. So yes, I hope that answers the question.
Any other question?
Yeah, I have two questions. Can I ask?
Please,
Yeah.
please go ahead.
Yeah. Thank you for your presentation. So my first question is to initiate, for example, in QIQT SPDC, one needs intense or strong laser intensity as compared to QIQT.
Yeah.
Moreover, you will have self-phase modulation effect apart from cross-phase modulation. So question is, any reasons why you have selected QIQT as compared to QIQT for SPDC?
Yes, yes. So one, as I have told, of course, if you look at the very first experiment that Slusser done in 1985, he used the QIQT medium in the atoms to generate the squeeze light. Okay, so but in late 90s, it was discovered by Scully and others that the configuration in the first configuration that Slusser used, it was a cascaded configuration. But the other configuration that we have used is a double lambda configuration. In that double lambda configuration, it was found, or it was predicted in late 90s, that it has enhanced Kerr nonlinearity actually. So that QIQT is enhanced in that kind of process, or that kind of configuration actually. That's why we used actually. On the other hand, whatever the available QIQT we have, we can't generate this kind of bright beams without using cavity actually. So the thing is, the configuration is what is giving us the enhanced QIQT nonlinearities. And if you compare with the power, of course, power is more actually. Power we are using 500. About 500 milliwatt, and on the other hand, SPDC people, they may use less than 100 milliwatt, but that is reasonable. That is not very, very critical, I would say, because what I want to have more power in my my twin photons, or the photons that twin beams that I want to create actually. So the answer to answer your question in one sentence is, this double lambda configuration gives us enhanced QIQT nonlinearities that allows us to generate the bright entangled beams with optimum lab conditions.
The second question, do you have any plans to use polarization degree of freedom of light in your experiments?
Yeah, not immediately, but recently, one leading group in China actually, they are very ahead of things actually. They mainly in quantum actually. They are one thing actually, the group has shown that, of course, the same system actually, if you dilute your pump a lot and then you can generate, or you can mimic the similar kind of experiment what people do in the SPDC setup actually, where you create a pair of photon, or you look at the polarization, correlation and all. Indeed, it is possible. I also plan to switch between discrete and continuous variable. I may do that in near future actually. Just with the same setup, looking at discrete and continuous variable quantum information.
Thank you.
Yeah, sure.
Okay, so I think we are running little out of time.